If you're an AI architect or engineer today, the question isn't if you can fine-tune a large language model. That's a given. The real challenge, the thing we all struggle with, is how to do it right. How do you find that perfect balance between getting the highest accuracy, not blowing up your budget, and, maybe most importantly, avoiding the headache of maintaining the system down the line? Well, that's exactly what we're going to break down.
Okay, so here's the plan. We're going to start with the fundamental problem, the fine-tuning dilemma. Then we'll look at the old-school brute force way of doing things. After that, we dive into the revolution that is PEFT, which is, changing everything. We'll compare the two big players, LoRA and adapters, and then wrap it all up by building your production playbook. So you've got this incredible, general-purpose AI. It's amazing. It knows about everything from ancient history to quantum physics. But how do you get it to understand your world? How do you teach it your company's lingo, your product catalog, and the specific way you talk to your customers?
Right. This is the multi-million-dollar question, isn't it? Getting this right is what separates a cool tech demo from a system you can actually rely on in production. And the answer really isn't about the model itself, it's about choosing the right architecture for fine-tuning.
Let's start with the big one, the heavyweight champion of fine-tuning, the full model approach. This is where you go all in, no holding back.
So, what does this actually mean? Well, think of your model as a giant skyscraper. Full fine-tuning is like deciding to rebuild the entire building just to renovate the lobby. You're literally changing every single one of the billions of parameters. It's unbelievably thorough, for sure, but you can just imagine the kind of resources, the GPU clusters, the storage you're burning through.
And this table really lays out the brutal trade-off. On one hand, yes, you get the best possible accuracy. The model becomes a deep expert, but look at the cost. GPU memory requirements are through the roof, training takes forever, and deploying these massive multi-gigabyte models is a huge operational lift. And rolling back a bad deployment, yeah, that's a nightmare.
And this is the part that keeps engineers up at night. Picture this. You deploy a new version where billions of parameters have changed, and suddenly the model forgets how to do a simple task it did perfectly yesterday. Where do you even start looking for the problem? It's like trying to find one specific screw you changed in that entire skyscraper. It's a black box inside a black box.
But what if you didn't have to rebuild a skyscraper? What if you could just, add a new super smart concierge team to the lobby and leave the rest of the building untouched? This brings us to a genuinely revolutionary idea, parameter-efficient fine-tuning, or PEFT.
Just look at that number for a second. This is a total game changer from a systems architecture perspective. We are talking about a 10 to 100 times reduction in the number of parameters you have to train, store, and manage. This isn't just a small optimization, it's a completely different way of thinking about the problem.
And here's the core concept. You take that giant pre-trained base model and you freeze it. You lock it down. It becomes this solid, immutable foundation. Then you just add these tiny surgical changes on top. You're not changing the core of the model at all. You're just adding a lightweight, specialized layer.
And you can see why engineers absolutely love this approach. Training is way faster, which means you can iterate more. Your infrastructure costs plummet, and rollbacks, because your changes are just these tiny, megabyte-sized files instead of giant models, reverting a bad deployment is trivial. It's just faster, cheaper, and a heck of a lot safer.
Okay, so we know why PEFT is so great. Now let's get tactical and dig into the how with a real-world production playbook. We're going to compare the two dominant methods you'll see out there, LoRA and adapters.
LoRA is, without a doubt, the workhorse of the PEFT world. The genius insight here is that you can inject these tiny, trainable matrices right into the model's attention mechanism, its core reasoning engine. The original model weights are never, ever touched. And that means the only thing you need to train, save, and version are these incredibly small new layers.
And this is the architectural pattern that makes LoRA so incredibly powerful. You have one giant base model loaded up in memory, and then you can dynamically swap in these tiny LoRA files at runtime. One model can power dozens of different tasks, a support bot, a sales bot, a compliance checker, just by loading a different few megabyte file on the fly. It's amazing.
Now, if LoRA is about teaching a model new skills, you can think of adapters as giving it entirely separate brains or knowledge domains. These are little neural modules that you literally slot in between the layers of the base model. They're specifically designed for clean, strong isolation between different contexts.
This chart makes the choice pretty clear. If your absolute top priority is keeping costs down and handling a bunch of different tasks, LoRA is your best bet, hands down. But if you're building, say, a multi-tenant system where you need a rock-solid wall between customer A's data and customer B's data, adapters are absolutely the superior architectural choice for that isolation.
So, how do we pull this all together into a real grand strategy? Let's stop thinking about it as choosing one or the other and start talking about how the most advanced teams build truly scalable, version-controlled AI systems.
Well, the most sophisticated teams don't pick one. They actually combine them. It's brilliant. They use LoRA to define how the model should act, its personality, its tone, its conversational style, and then they use adapters to inject what the model should know, the specific knowledge for finance versus the knowledge for law. This lets you update the model's behavior and its knowledge base completely independently of each other.
The result is pretty much an engineer's dream deployment pipeline. Your massive base model is just a static, unchanging asset. Your customizations, the LoRA and adapter files, are treated just like any other piece of code. You check them into Git, run tests on them in your CI/CD pipeline, and deploy them independently. A rollback is no longer this huge, terrifying event. It's as simple as changing a config file to point to an older version. It's that easy.
So if you only remember one thing from all this, let it be this. Full fine-tuning gives you max accuracy, but it also brings maximum pain. For almost everyone building real-world applications, PEFT is the answer. LoRA is your go-to default, adapters are your specialists for isolation, and the whole PEFT approach is what lets you build fast, safe, and scalable AI systems.
And that right there is the ultimate takeaway. This isn't just about tweaking some machine learning algorithm anymore. It's about designing a robust, maintainable, and powerful system. This is what software architecture looks like in the age of AI. So the real question to leave you with is, what architectural patterns are you going to build?